Okay, guys, in this lesson, we're going to be focusing on electron configurations and also these things called ground states and excited states. But there are a couple of things associated with this lesson I should mention now. The first one is there's going to be a little project called My Element Page. They're going to be due on Monday, so you'll have the whole weekend to work on them. And in class, when I see you guys, ask me and I will show you an example. There's no problem with me showing you an example. And I'll give you a handout that'll outline the information that you'll need to include. And also associated with this lesson, we have a quiz. So there will be a quiz on everything you've learned so far associated with this lesson. So make sure that definitely by the time that you see this video, you'll be wanting to study for the quiz because most likely it'll be the next day. All right, so what are electron configurations is our aim. Copy down the information in this do now. Don't solve for the identity of the element yet, but just copy down the information into the classwork section of your binder and we'll work from there. So here is where we will start the lesson today. There's a couple of parts. The first part is just electron configurations in general. So speaking of electron configurations, the model that's really best for visualizing these configurations, the one that we use on our reference table, is actually the Bohr model. It's really great because it has these really specific orbits. Although it's not the model that we use today, the specificity of those orbits, which you can see represented down here in this diagram, the specificity of those orbits really helps us visualize where those electrons should be in the atom. Here are some notes that you definitely want to copy down. Electrons exist inside energy levels, which is another name for orbit. There are 4 major energy levels that you need to know about for sure. We have N1, N2, N3, and N4. N1 is this orbit, the one closest to the nucleus. N2 is the orbit just above N1. N3 is the orbit just above N2. And N4 in this atom is not pictured, but it would be just above N3. And then another note that you need to know, that you have to have in your Cornell notes, is that energy levels fill from the lowest energy level first. So N1, this orbit, this energy level, this guy is going to get the first electrons, and they'll fill from there. So after this guy's full, then we'll fill the second orbit, and then once that's full, we'll fill the third. That's the basic process. So full is relative depending on the orbit that you're in. So lower orbits can hold lower numbers of electrons and higher orbits hold higher numbers. So it's referenced here in this diagram. In energy level 1, 2 electrons will fit. In energy level 2, 8 electrons will fit. And in energy level 3, another 8 electrons will fit. Depending on your model, it might be 18. So here are the rules you should write down. 2 electrons can fit in the first orbit, 8 in the second. For our purposes, memorize 18 can measure in the third, and 32 can fit into the fourth orbital. This could be tedious to memorize, so if you're any good at math, and I know some of you are, there is a very simple mathematical expression that can help you avoid memorizing the number of electrons that fit into each orbital. So n, as I just discussed, represents an orbit. So if you have n1, n2, n3, n4, you just take that number and you plug it in for n. So in n1, you're basically performing the following operation. 2 times 1 squared. In n2, you're doing this, 2 times 2 squared. In n3, it's 2 times 3 squared. And in N4, 2 times 4 squared. So 1 squared is 1 times 2 is 2. 2 squared is 4 times 2 is 8. 3 squared is 9 times 2 is 18. Oh, do you see what's happening? 4 squared is 16 times 2 is 32. And these are the maximum numbers of electrons that can fit into each orbital. So if you memorize this expression, you should be able to figure out quickly how many electrons fit into each orbit. All right, so then I was talking about this diagram. Electron configurations are given on your periodic table, and the diagram to the right is a pretty good representation of the electrons in an argon atom. Argon has the electron configuration of 288, which we can get right off of your periodic table. Add an exclamation point there. And once you have that 288, you can fill in electrons into the model. Put 2 electrons in the first orbit, put 8 electrons in the second orbit, and put 8 electrons in the third. So one thing that's interesting here is that some of you maybe were expecting 18 electrons to be in the third orbit, just like I have up here, but it says 18 electrons will fit. It doesn't mean that you have to have 18 electrons. So whatever it says on the reference table, whatever it says on the periodic table for that particular orbit, regard that as true. It's just that you can't go above 18. It doesn't mean that it has to have 18 electrons. So here's this concept of excited state versus ground state. This was referenced when we first started talking about Bohr. And we would say that Bohr would disturb the atoms or excite them by adding electricity or by adding heat, and then that would make them glow with a predictable color. So that this experiment is being referenced again here with neon atoms and lithium and sodium. So it's going to reference ground state and excited state. So here we are with neon. We'll just start on the top left. Neon, it has a ground state electron configuration of 2,8. Now, ground state is what you'll find on the reference table. So whatever is listed on your periodic table, that's always ground state. And if you look up neon right now, you'll see that the ground state for neon on your periodic table is 2,8. And if you were going to draw that into a diagram, it would look just like this. It would have 2 electrons in the first orbit, and it would have 8 electrons in the second. So this is definitely a ground state diagram for neon. Now, if you look up neon like we just did, and you see 2,8 as the ground state, but then you see it written a different way, and instead of it being 2,8, it's going to say 271. I'll zoom in just to highlight this a bit more. So instead of 2,8, it says 271. That is not a ground state configuration. And one of the ways you can tell is that you have seven electrons here and you have 1 electron there. And this 1 electron actually could fit into the second orbital if it wanted to, because this orbital can hold 8 electrons. And it doesn't mean that it has to, but if they're already filling another orbital before this one's full, then that's definitely excited state. So this guy right here, this electron that should be in the second orbital, this electron is proof that we're in excited state. If you want to know what that would look like, it would look like this. Here's your 2, here's the 7 in the second orbit, and there's 1 in the last. So what I think has happened is that this electron in the third orbital probably used to be down here at one point, and then it absorbed energy and jumped up to that outer orbital. So it changed the configuration to be 271 instead of 2,8. So that's what we mean by excited state. So this is definitely an excited state. So it is okay for an element to be in an excited state. It's very natural that it will absorb some energy and that an electron will jump up to a higher level. But what is also natural is that that electron will then subsequently fall back down to the ground state. So although it's natural for a ground state electron to move up to an excited state, it's also natural for it to move back down to ground state. And in that process, it will release the energy that it had absorbed in the form of light. And depending on the element and its electron configuration, you're going to get a different color of light for different elements. And that's because these different configurations are going to lead to different amounts of energy being absorbed, which will lead to a different amount of energy being released, and that's going to translate into different colors. So here are some things that you're going to need to know for this entire process. Electrons move between energy levels if they have just the right change in energy. So not every amount of energy is going to work. The principal energy level closest to the nucleus has the lowest energy, and as you move away from the nucleus, levels increase in energy. When an electron is in the lowest level possible, we consider that ground state. When an electron is in any level above ground state, we consider it excited. The excited state is unstable, and the electrons move back to their ground state. That's considered natural as well. Electrons move between energy levels depending on the energy they have. And electrons absorb energy in the form of heat, light, electricity, and they always move up when they absorb energy. And then electrons lose energy in the form of light, and they fall down, so they always fall down a level when they release energy. I think that these last two are of particular importance for you to definitely know. All right, so your pair up is just going to be copy down this very basic table, Bohr models in their ground state on the left-hand side, Bohr models in their excited state on the right-hand side. It's going to be the same elements in each side, lithium, carbon, oxygen, chlorine. This should be relatively large in your notes because you're going to have sketches in the boxes and you don't want to be crowded. The summary we'll work on in class tomorrow, but copy them down for now and don't solve them. All right, thank you.